natural number set n, set of non-negative whole numbers, W, set of integers, all of these sets were not filled actually, but we got our set Q of rational number set, which has got all the characteristics of the algebraic structure, and therefore it is a field. But then mathematicians again thought of expanding their uh, set of number system for some reason or other, probably to accommodate the numbers like pi, √2, √3, the set of irrational numbers which were also present. Initially it was thought that the set of rational numbers was complete set, but later it was found that no, it is not. So later they designed the set of real numbers, and you know that the set Q is actually the subset of set of real numbers. Set of rational number is a subset of set of real numbers. And if Q is a field, so is R. Okay, the smaller set is field, so the bigger was obviously a field. So if this is your R and this is your Q, if this smaller set is field, the bigger one is obviously a field. So set of real numbers is a field actually. And not only this, it can be easily seen that set of complex numbers, which is the largest set of numbers so far designed, this is also a field. Okay, so this structure field is actually very important to know the idea, to get the idea of the topics like matrices, determinants, and vector space. So whenever I'll be starting the course of PSM 101, you will be seeing that I'll be repeatedly saying that I'll repeatedly utter the word field, and then probably will not be facing any trouble to understand what field is actually. Now let's talk about the matrix. Okay. Let's talk about matrix. Now, for my today's class, we shall concentrate on a 2x2 matrix only. Okay. Let us consider a set. Let us consider a set M 2 cross 2, and we are writing inside the bracket F. This set we'll read this particular thing as M2 cross 2F. What does it mean? It means that the set of all 2x2 matrices, okay, whose elements are taken from a field. Now you see, if initially I gave you this particular notion that, yeah, this is a set of all 2x2 matrices whose elements are taken from a field, you could have immediately asked me what field is. So therefore, I taught you what actually the field is. What does it mean? It means that suppose I want to give you a matrix like this: 1, 2, 3, 4. It is a 2x2 matrix. Okay. But whenever I give you a matrix like this, these elements 1, 2, 3, 4, do not consider these elements to be the element of set of natural numbers. You have to consider the complete set which is the set of real numbers. So we shall consider these elements 1, 2, 3, 4. All these elements we are considering to be belonging to the set of real numbers. So actually this matrix is belonging to M2 cross 2, whose elements have been chosen from the set of real numbers. Just try to identify and or try to focus on what I'm saying. Okay, if you have any doubt, you can unmute yourself and you can ask me. If someone wants to give me a matrix like 1 plus I, 2 plus I, 3 plus I, 4 plus I, he is giving me a matrix which belongs to the set M2 cross 2, whose element have been chosen from the set of complex numbers. Because each of these numbers, 1 plus I, 2 plus I, 3 plus I, 4 plus I, all these numbers belonging to the set of complex numbers. And you know that set of real number is also a field, set of complex number is also a field. So therefore, now onwards, whenever we'll talk about the matrices, whatever its order is, we'll always think of the situation that the matrix has been constructed by choosing the elements from a respective field. Remember, I am giving you the prerequisite which is needed for our actual topic of BSM 101. Okay, so you are actually getting the taste of the prerequisites. Whenever the actual class will start, I'll not be discussing, I'll not be explaining these things again. So whenever so for example, if someone wants to talk about a matrix of this type, A11, A12, A1J, A1N, A21, A22, A2J, A2N, AI1, AI2, AIJ, AIN, and AN1, AN2, ANJ, ANN. If someone gives you a matrix like this, remember, he is choosing his matrix from the set MN cross N, where these elements are elements taken from a field. This field can be the set of rational number, can be the set of real number, can be the set of complex number, but should not be the element, should not be considered as an element of integer set or natural number set or non-negative whole number set. Okay, so we have to be very careful about what elements we are choosing to construct the matrix. If someone gives you a matrix of this form, A11, A12, A1J, AM1N, A21, A22, A2J, A2N, AI1, AI2, AIJ, AIN, AM1, AM2, AMJ, AMN, then always remember that he is choosing his matrix from the set M cross NF. What is the difference? Difference is there. This is N cross N. This is M cross N. So N cross NF is the set of all square matrix of order N whose elements are chosen from a field, and M cross N F is the set of all matrices, be it square, be it rectangular, whatever, set of all matrices of order M cross N, whose elements are chosen from a field. We call these matrices, we denote these matrices by capital A. And to reduce our hard work on the matrices, okay, so we actually have designed a very symplectic form by which we can avoid writing this huge gigantic form of the matrix. What we do is that we try to locate the general element Aij, which is present in the ith row and jth column. And to represent capital A, we simply write this general element Aij, and we put it inside a parenthesis, and we give it an order. We'll call it to be a matrix which belongs to M cross N F. Whenever we write this, that means we are actually considering the entire matrix of this form. It actually reduces our time and labor to represent a matrix. So in similar manner, if I want to call this matrix to be, say, A prime, to represent it in a very simple form, what we need to do, we consider the general term Aij. We keep this term inside the parentheses, and we just put the order outside, and we call that this belongs to the set Mn cross Nf. But if someone simply writes Aij belongs to M cross Nf, or if he writes Aij belongs to Mn cross Nf. Okay, if someone writes like this, then it is wrong. Because see the difference. Here you have considered the element only. Here I have considered the element, a general element, putting it inside a parenthesis and setting the order outside. So you have to be very careful about what notation we are using to represent the matrix. Okay. So matrix, we have known from our previous session what is field, how to construct matrix by choosing elements from a field. And now let's talk about what is determinant. What is the difference between determinant and matrix? Difference between determinant and a matrix. Okay. This is actually very important. And now, since I'm taking the class, I have not asked you any questions. So I want you to write in the chat box. Don't unmute yourself. Write in the chat box and let me hear from you. What do you think about this answer? Or what do you think of this answer? What is the difference between determinant and a matrix? Write in the chat box. You can, if you don't want your answer to be visible to all the participants, you can directly message me through the dimensions. What do you mean by dimensions, Harshit, CSE? What is the meaning of dimension? Sign. Okay. So if I write, someone is writing magnitude. Okay. Dimension, sign, magnitude, magnitude. Means row and column can be different in matrix. Means the numbers, but determinant is, yeah, someone whose name is, okay, Adarsh Sharma. Yeah, two of the students have written it correctly. I don't want any more replies. Let us talk about the first three replies that have been given to me. First of all, let's talk about the dimension. Let's talk about the sign. Let's talk about the magnitude. I do not know what do you mean by the dimension. Okay. What do you mean by the dimension? I asked you what you couldn't define what dimension is. You can unmute yourself and you can tell me what dimension is. By sign, what do you mean? I don't understand. Because if I write 1, 2, 3, 4, and if I write 1, 2, 3, 4, now with respect to everybody, all of us know that this is a matrix and this is a determinant. Now, try to make me understand what do you mean by this single word sign, which will distinguish between a matrix and the determinant. Someone has written the difference is magnitude. What do you mean by that? What is the definition of magnitude? What is the magnitude of the matrix and what is the magnitude of the determinant? Is there any term like magnitude of the matrix and magnitude of the determinant? No, there is no such term. So these particular answers that have been given, they do not have any meaning at all. But two of the students, very roughly speaking, they have said it correctly. One of the students said that matrix is a kind of arrangement and determinant is a kind of unique number. Determinant is a kind of unique number. Okay. In arrangement, in computer engineering, this is called array. It is called array. So in matrices, in computer science, it's called arrays. You will learn this in your programming language classes. And determinant is a unique number. Yeah, that particular reply I can consider. Now, the student who has given me this reply, or the students who think that, yeah, this is the correct one, I am to them, I am asking another question. Why do we say always that to every matrix there is associated a determinant? Can you explain this thing to me? Why do we say to every matrix there is always associated with a determinant? To every matrix, a determinant is always there. I think writing in the chat box is not a good option. You can unmute yourself.
Sir,
yes, tell me.
The determinant is a real number.
Mm-hmm.
It is not a matrix. Actually, determinant only exists for a square matrix.
Yeah.
So the determinant is that single value in the determinant, and the inverse of matrix will exist only if the determinant is not zero.
I'm not asking about inverse. You have said that, okay. So you have said it correctly, that why do we say always that to every, okay, I probably missed this word, to every square matrix there is associated determinant. Why is it so? Matrix is a kind of arrangement. It's a different thing. It's a structure. Matrix is a structure where some things are arranged in proper fashion, in row fashion and column fashion. It's a number. How can I correlate this number to this structure? What is the logic behind it?
The determinant is an operation which
okay, wait, you can Google it and you can ask me, give me the reply. We do not have any problem with this. But okay, what determinant is a kind of operation.
Operation, sir.
Can be
What sort of operation? Determinant is the addition operation or multiplication operation?
No, sir. It is an operation done on the matrix that produces a definite number.
Okay. So by operation, do you mean function?
Yes, sir.
Okay, so let's not waste time. Probably the student who is replying me, maybe he has Google searched or maybe he knew. That doesn't it is not an issue for me. But whatever, if he understands correctly by what he is saying, then let me talk about this point and he will verify by himself whether he meant what he said. Okay, first of all, in the previous week, in the last week, the teacher talked about the function, and he said that we can define a function from a set capital A to another set capital B. We can define a function where capital A set is actually the domain and capital B is called the codomain or range. Okay, domain and codomain. Now, what you are doing is that, and what I'm going to do is that the matrix that I have chosen now, as you have said that to every square matrix there is always associated determinant. I am choosing the set, my domain to be mn cross nf. Okay, and from this particular set to the set of real number, I am defining a function f which is given by this symbol. Just try to correlate what I have written. So this is the thing that I have considered. In place of f, I have written a modulus sign type of thing. In place of a, I have written this particular set, which is actually the set of square matrices. And in place of b, I have considered the set of real numbers. Now, the teacher told you that whenever we define a function like this from a to b, what we do, we define the function in a particular fashion. We choose the element x from the set A, we apply f on the set x, and we get an element y which belongs to B, and x belongs to A. So by keeping this in mind, we are going to choose a square matrix A11, A12, A21, A22. This is the element of the matrix mn cross nf. Okay, so it is 2 cross 2. Actually, I am considering here 2 cross 2 for simplicity. We can always generalize the thing to any time, any higher order. So 2 cross 2, say for example. And on these, I'm going to operate this function. So this operation, what we need to do, we consider the matrix inside the, this function is what is a kind of is a kind of machine in which the input are given and the output comes out. So whenever we are choosing the matrix from this particular set of all matrices of square of order 2, we are putting this element inside that machine, which is given by the modulus sign, and the output is given in a particular fashion. Okay, now whenever we define function, we have come across that we can define the function by fx equal to x square. We can define the function by fx equal to sine x. We can define the function as fx equal to e to the power x. There are many different ways by which we can design the function. Here, the particular way by which this is designed is the following. We simply write it as, we just do not consider the bracket. We consider the modulus sign only, and we simply define this element as a11, a22 minus a12, a21. Okay, and this is nothing but a number which belongs to the set of real numbers. Okay, so determinant is a kind of function which, when operate on the square matrix, gives you a number. So if this is so, the student who just now gave me the reply, determinant is a kind of operation which acts on the matrix, he is right by what he actually said with respect to the determinant. Yes, the thing is that determinant is actually the number which is actually behaving in this particular fashion. And obviously, for third order matrix, for fourth order matrix, we can generalize this particular definition in a different uh, different way. Actually, the ways are not different. There is a very intricate reason for which this is done. I mean, someone could have asked me at this point, oh, why this function is defined in the way it is defined. Why not it is defined in the following way? A11, A21 minus A12, A22. It could have been defined in this way also. But why it is always in this cross product type of form? Why not in this form? Okay, this is a very legible question. It's a legitimate question, but I'm sorry to say that I'm not going to reply to your question right now, because it is beyond the scope of your syllabus. To understand this particular, I mean, reason, you have to know, you have to have some idea about some other algebraic structure called group, which is not there in your syllabus right now, but fortunately you will be learning this group theory in your fourth semester course of CSE program. So let us keep this discussion for some later topic, okay, not for this semester. So remember this question. This is a very legitimate question. Why it is not defined in this particular manner? Why it is defined in the cross product type of, but it is defined in the cross, for some reason or other, it is defined in a cross product type of form, and we have to digest it for the time being. So determinant is actually a unique number which is always associated with a kind of arrangement. And when someone wants to generalize the thing, what he, so for example, third order determinant, then he actually consider his domain to be this M3 cross 3R. He operates this function on it, and the result is R. If someone considers a complex field, he will be getting a complex number. Generally, is quite obvious. If someone considers a rational number set, he's actually going to get a rational number. So what is happening, if I want to generalize in a more generalize in a certain way, we are considering a matrix of order n cross n, whose element has been designed from the field F, and on which I'm operating the function delta, so that it gives a number which is from the field itself. Okay. And you know this third order, how third order determinant is actually defined. I'm not going to write it here. You can verify it quite easily, that A11, A12, A13, A21, A22, A23, A31, A32, A33. How it is defined, you know very well. Okay. Or if you want to write, if you want me to write it for the sake of completeness, I'm writing it in the following manner. And for this type of determinant, for fourth order determinant, that means if I choose a matrix of order 4, you can see, you can check in any book that there is a kind of method which is called Laplace method, or probably you have heard about Kio's method in your school days CBSE book. These methods are actually applied to to calculate the determinant of a matrix of order 4. But we are not interested about these methods because these are not in the syllabus. Even if you do not, if you cannot recall what these methods are, and if you have not gone through these particular methods, then it is not a huge problem. It is not a huge burden to all of us. Okay, so you can always neglect this kind of thing. My basic prerequisite is that you have to understand the notion of the difference between the matrix and the determinant. Now I shall suggest you to go through any book that you have studied in your school days. You go through any book and you just revise the properties of determinants and matrices. Okay, you just revise the properties, and these properties are actually sometimes will be required to study the topics of module 5 and module 6, module 4 and module 5 of our syllabus. Okay, so now I'm going to talk about the book that you can that I'll be following to for the study of BSM 101. The page that I was sharing with you, I'm going to show its title page. I hope that you are able to see it. The name of the book is called Linear Algebra by Stephen H. Friedberg, Arnold J. Insel, and Lawrence E. Spence. This will be my textbook. This is going to be my, this is my textbook for covering module 3, 4, and 5. Okay, so I'll be discussing problems from this particular book, and the publisher of the book is Prentice Hall, and this is the ISBN number. You can note it down. This is available in market. You can get a copy if you want. From college, what book you have been given, I do not know. But I always suggest that if you have a broader goal of learning artificial intelligence, deep learning, machine learning, that you are going to encounter in your subsequent semesters in your core engineering program and in quantum computing also, then you have to digest this particular book. No other book can help better than this. No other book can serve better than this. I will share a note day after tomorrow to you. That note will be those particular pages will be split from this particular book, and I'll share with you, and you will get to see that what is written in determinant chapter of this book, what extra things are written in the determinant chapter. But for now, you can go through any of your school days book and you can revise the properties of the determinants. If I try to give a lecture on these properties, I think it will, I mean, you will become bored. So I'm not going to discuss it right now. And for the first two modules, 1 and 2, the books that I'll prefer will be told to you later on, because these topics, which is actually very diverse, they and the book in which these topics are there is so voluminous that you may become discouraged by if I give those books to you. So I shall not prefer. I'm not going to give names of those books. I will try to prepare a note on this two particular section, and for you, my personal note, and I'm thinking of sharing that note with you at some point of time. But I will suggest that if you want to excel in computer programming, please digest this particular book and you will be benefited. If you do not read this book, You will face difficulties in every phase of your engineering course. Okay, so these are the topics that this book will cover: vector spaces, linear transformation in matrices, elementary matrix operation, determinants, diagonalization, inner product space, and appendix is there, canonical forms. Except canonical forms, everything else is there in our syllabus. All the chapters starting from 1 to 6 is there in our syllabus. So we have to digest this particular book. Okay. Tomorrow we have a class I have a class with you at 1:40. There I'm going to talk about the relevance of inverse, why matrix inverse is important, and how actually we calculate the matrix inverse. One obvious way is to take the help of determinant, as a particular student has told me just now that a few minutes ago. The determinant helps me to find the inverse of the matrix. But my question is why the inverse is the definition of inverse that we have to actually apply. Why the definition is given in this particular way? Why it is so? Why we consider the adjoint of the matrix and we divide it by data? Why we do this? That I'm going to explain. Why inverse is important, that I'm going to explain. How can we find the inverse of the matrix without the help of the determinant, that I'm going to explain in my tomorrow's class. Hope you have understood what I wanted to convey to you. And after some days, your classes will be separated. So those students who will be in CSE section B, they will be attending my class, and the students who will remain in CSE section A, they will attend Kaustubh sir's class. Okay, but later on. And for CSE section A, I must say that Kaustubh sir also prefers, KD sir also prefers this particular book. This is our actually joint venture. So linear algebra book, Sari will also follow. So you don't have to worry that the other teacher will follow another book, and here in CSE section B, you will be following this linear algebra book. That is not the thing. Both of us will be following the same book. So you don't have to worry about it. And with this, I'm going to conclude my today's session. Hope you have understood the basic requirement that is needed to cover the topics of BSM 101. Hope to meet you tomorrow at 1:40. Till then, bye. Okay. You can leave the
Thank
classroom
you,
now.
sir.
Thank
Yes.
you, sir.
Yes.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Bye, sir. Bye, sir.